Chapter 6, Part 2, Metal carbene or alkylidene and metal carbine complexes. The concept of M double bond C between a transition metal and carbon constitutes one of the most important elements in the field of organometallic chemistry. M double bond C catalysts were used in the polymerization reaction. The notion of a metal-carbon double bond was first proposed by Fischer in 1964 with the synthesis of the complex WCO5-C-phenyl-O-methyl. This preparation starts from a complex WCO6 plus metal lithium. We will have addition of CH3- to the complex to have a complex containing carbonyl and methyl. Then the methyl will migrate to attack CO, so we will have CO5WCOCH3, which was in resonance form with another structure CO5WCO-CH3. To stabilize the O-, we use trimethylhexanium that plays a role in the stabilization of orbitals of carbene by donation of the lone pair from oxygen to the carbon of carbene. In the late 1973, another organometallic chemist named Schrock, working at the Central Research Depot, prepared the first early transition metal complex with a metal double bond carbon, including a number of tantalum complexes. He followed the same procedure as Fischer. To note that Fischer prepared M double bond C for transition metal, the late transition metal, and Schrock prepared the first metal double bond C for the early transition metal. But Schrock followed the same type of reaction as Fischer. He used alkyl lithium and he obtained unstable intermediate that by alpha elimination give Ta, L3, and we have elimination of alpha from the fifth ligand plus dissociation of one ligand. So in total, we have 4 ligands starting from 5. We have 4 ligands, 3 remains the same, and 1 ligand is submitted to hydrogen elimination, and we have release of other ligand. So Schrock used the same procedure as Fischer, and the metal carbene is called Schrock metal carbene. So what is the difference between Fischer carbene and the Schrock carbene? And they follow the same type of reaction. We will see later that the experiments prove that we have different reactivity of M double bond C in case of Fischer and Schrock. Second, the structure bonding between M and carbene differs from Fischer type to Schrock type. To study the structure of metal carbene, we have to study first the structure of the carbene ligand itself. Carbene is a molecule containing a neutral carbon with two unshared valence electrons. They are uncharged and electron-poor molecular species. Carbene has two forms, the singlet carbene and the triplet carbene. In the singlet form, the two valence electrons are in the same orbital with opposite spin, and in the triplet carbene, we have two single electrons in two different orbitals, and these two electrons are of the same spin. In the carbene, the hybridization form is sp2, and we have three hybrid orbitals. Two of the hybrid orbitals are involved in the bonding with R groups, and one sp2 hybrid contains the lone pair. In the triplet form, we have two hybrid orbitals involved in the bonding with the R groups, and we have another sp2 orbital containing one single electron. If the type of hybridization of carbon in carbene is sp2, so we will have a p orbital, which is a pure p orbital. In case of the singlet carbene, this p orbital is vacant. And in case of the triplet form, this orbital p contains one single electron. So if we consider carbene as a ligand in the singlet and the triplet form, we can say that in the singlet form, we will have one type of bonding to the metal M from the lone pair of the carbon of carbene. But in the triplet form, we can have two types of bond, one from the orbital sp2 of the carbon of carbene, and the second type of bonding is from the p orbital of carbene. So the key difference between Fischer and the Schrock carbene is first the nature of ligands on M, and second is the nature of the groups on the carbon of carbene. Consider the structure. This is a metal carbonyl ligand bound to a carbene, and the metal M has d orbitals in all directions. The metal M in this case is electron poor, and this is due to the presence of the pi acceptor CO ligands. To remember that carbene has a p orbital vacant that needs to be filled. So we have two possibilities. The first is the pi back donation from M to the p orbital empty, and the second is the donation from p orbital of N to this vacant orbital. And since M is poor in electrons, so the possibility of the pi back donation from M to C is very weak. In this case, we will have donation of electrons from p orbital of the Lewis base atom N to the carbon of carbene. And in this case, the double bond is between C N and not between M and C. So the form is M single bond, double bond, N, but this form has a resonance form which is M double bond C single bond N. So we know that in this case the MC bond is single even we draw a double bond. In Schrock carbene, the carbene is in the triplet form. So we will have one bond from the orbital sp2 of carbon to the metal, and we have another bond from the single electron present in the p orbital to the empty d orbitals of M. So in this case, the M double bond C is clear. So as a conclusion, in Schrock carbene, we have a real M double bond C, and in Fischer carbene, we have a bond which has a character of M double bond C. So according to this difference in the structures of the metal carbene, Fischer and Schrock, carbene ligand in case of Fischer is a neutral ligand 2 electron donor, and in Schrock is dianionic ligand 2 minus and 4 electron donor ligand. The experiments showed difference in reactivity between Fischer and Schrock carbenes, and this is due to the difference of the structures. In Fischer carbene, the carbene is sigma donor to M via the lone pair, but the orbital P is still empty and cannot accept electrons from M by buyback donation because the M center is poor in electrons. Even this orbital is partially filled from the groups of carbene, but this leaves this group electrophilic. So in reality, the true M double bond C bond order in case of Fischer carbene is much less than 2, as observed experimentally by X-rays crystallography. So this favors the form M single bond C double bond N, where the double bond is between C and N and not between M and C. As reactivity of Fischer carbene complexes have electrophilic character of p orbital of carbon. So this site is susceptible to nucleophile attack. And the metal M has a nucleophilic character, so it's submitted to electrophile attack. In case of Schrock carbene complexes, we have the inverse reactivity. The p orbital of carbon is filled and has nucleophilic character, so electrophiles have the tendency to attack this filled orbital p. In Schrock complexes, The metal center is usually poor in electrons and has around 12 to 16 electrons. So there are several empty orbitals, very attractive to any nucleophile that can access the metal center d orbitals. So as a conclusion, the difference in the structures of the metal carbene between Fischer and Schrock results a difference in the reactivity. This table is a summary of the properties. For example, the nature of carbene carbon in Fischer, electrophilic, in Schrock, nucleophilic. The R groups in Fischer should be donor, so we should have a Lewis base atom. In Schrock, the R groups should not contain an atom Lewis base, so R group is alkyl or hydrogen. The metal in Fischer are in general the late transition metals, and in case of Schrock are the early transition metals. The ligands around M in case of Fischer should be pi acceptor in order to pump the electron density of M. For example, the carbonyl ligand. In case of Schrock, these ligands should be donor of electrons. As electronic counting, in the Fischer-Carbene complex, the carbene is neutral, 2-electron donor. In case of Schrock, the carbene is dianionic, 4-electron donor. To make the difference between Fischer and the Schrock carbenes, in organometallic, for Fischer complexes, we use the notation Fischer-Carbene. And for Schrock, we use the notation Schrock-alkylidine complexes. But in some books, they use the same notation. Counting of electrons in Fischer metal carbene and Schrock metal alkylidine. In the two cases, you can consider carbene as a neutral ligand 2-electron donor or as dianionic 2- 4-electron donor. But due to the structure of Fischer-Carbene, we prefer to use the ligand as a neutral 2-electron donor and in Schrock-alkylidine as dianionic 4-electron donor. Consider these complexes. The first question, what is the nature of this metal carbenes? In the first, we have a metal center and we have on the carbon of carbene, we have Lewis base. So this complex may be considered as Fischer-Carbene. But at the same time, around Re, we have donor group and acceptor group. So the presence of 2CO will decrease the electron density on Re. So this metal carbene can be considered as Fischer type. In the second figure, we don't have R groups on the carbon of carbene having lone pair. So this is, from this side, this is Schrock type. And also on TA, we have groups that are strongly donor. So this is a Schrock type. In other complexes, we will find that the metal carbene has percent of Fischer type and percent of Schrock type. And we will see that these examples in details in the exercises. So we return to the electronic counting. The oxidation state of Re, if we consider this carbene neutral, we have two carbonyl neutral and one Cp minus, so we have Re plus 1 d6. Cp minus is 6 electron donor, 2CO 2 times 2 4 electron donor, and we have the carbene, which is 2 electron donor. So in total we have 18 electrons. In the second figure, which is Schrock type, the carbene is considered as dianionic 4 electron donor. So 2 minus and 1 minus Cl and 2 minus Cp. So Ta is Ta5. So D0. We have 2 Cp minus 2 times 6 12, 1 Cl minus 2 electrons, and the carbene is considered as full electron donor. So in total we have 18 electrons. What would happen if we consider this carbene neutral 2 electron donor? In this case, the oxidation state will be Ta3, so D2, 2 Cp minus 12 electrons, 2 times 6, 1 Cl minus 2 electrons, and 1 carbene, which is considered the neutral 2 electron donor. So in total, we have the same number, 18 electrons. So in electronic counting, you can consider the carbene neutral 2 electron donor or dianionic 4 electron donor. This is the same type of calculation, but in the structure, you have to make the difference. Since we have difference in structure between Fischer and Schrock carbenes, in Fischer we have practically M single bond C, C double bond X, and in Schrock we have M double bond C, single bond R. So 13 carbon NMR can be a potential method to distinguish between these two types of carbenes. And we know that the chemical shift of carbene carbon is usually quite sensitive to the chemical environment, the electron density, and the bonding factors. But the experiment proved that the NMR data sometimes are useful, but generally won't allow to identify between these two types of carbenes. So the best method to make the difference between Fischer and the Schrock carbene is the X-ray diffraction on crystals. After the discovery of the metal carbenes and metal alkylidenes, Fischer and Schrock continued their research on the carbenes, and they prepared by the same way the metal carbenes and the metal alkylidenes. Carbenes and alkylidenes are treated as trianionic ligands, 6 electron donor, and these ligands are very strong donors, as might be expected, due to the low electronegativity of carbon and the 3- charge. They prepared metal carbine where the carbine is bound to one metal center and in this case is 6-electron donor. Carbines are also good bridging groups for two or several metal centers. Like in this example, we have C double bond Re and we have one single bond Re. So we can assume that carbine is 4-electron donor to the first metal center and 2-electron donor to the second. So in total, it's 6-electron donor. But also due to the delocalization of the bonds, we can assume that carbine donates 3 electrons to each metal center.